We're gonna get started. So I want to first thank you all for coming to our final mini med school session of the season. It's been a really nice time being able to lead with my co-leader Rochelle, and it's really just been a joy having all of you guys here every week with us. And so today I'm pleased to announce that we're having our session on immune response and immunotherapies. We'll be starting off with one of our MD PhD students, Emily Kounlavong, and then followed by our faculty speaker, Dr. Snow. All right, thank you.
Hi, everyone. I have the honor of introducing our two speakers. First is Emily Kounlavong, our fifth-year MD PhD student at UNC. She is pursuing both her medical degree and PhD in the Department of Pathobiology and Translational Science. Before coming to UNC, Emily studied chemistry at the University of Tennessee and conducted research at the Vanderbilt University Medical Center. She is currently a student in the lab of Dr. Billy Kim, where her research focuses on cancer biology and the immune system, particularly how the body cells and surrounding tissues interact in bladder cancer. In addition to her scientific work, Emily is involved in a number of mentorship, advocacy, and outreach organizations, both at UNC and beyond. We're really excited to have her here today to share some more about the immune system and the important role it plays in protecting our health.
All right, thanks everyone for coming. It's great to be here to talk to you all a little bit about the immune system and to give you kind of a teaser before Dr. Snow's talk. So I wanted to talk to folks briefly about the immune system and kind of just give a general overview. And then if you have questions, I'm happy to answer them throughout too if something doesn't make sense. So feel free to stop me. So first of all, I wanted to just kind of highlight a few of the organ systems that are associated with your immune system. So when we say it's one system, it's actually kind of all over our body. A few that are highlighted here are your thymus, which is right here at the top part of your chest. Folks often know about your lymph nodes that are all over your body. And then the lymph vessel that also connects them. And then you also have your spleen and then also your bone marrow. And so as you can see on the slide, your bone marrow is generally where your immune cells are created. They then go to the thymus where they mature. Those are where they meet, and I kind of think of the lymph nodes as maybe the meeting rooms is where they go to have the conversations. And then you also have your spleen, which for the immune system, one of the jobs that it does is to help us filter the blood as well. And so when thinking about the immune system, I like to think of it as almost two halves of a whole that are working together. And so you have your innate immune system, which folks generally think or associated with being very fast to respond, technically being very generic, and then also referred to as no memory or doesn't remember things. And when you're thinking about the innate immune system, you could think about an allergic response. So that's an immediate fast response. And then for your adaptive immune system, so this one's a little bit slower, but it's actually more precise. So it takes a lot of time to make sure that it's targeting the right antigens or the right pathogens. Then it also remembers. And so when you're thinking about the adaptive immune system, you can think about vaccinations where your body is learning how to attack certain pathogens so that if you were to ever get sick, it would already know how to fight that pathogen. And so one of the hardest jobs that your immune system has is actually telling self from non-self. So a lot of the times I like to think that the cells are thinking, hey, is this me or is this not me? And so there are sometimes foreign materials that our body is exposed to that includes bacteria, viruses, or transplanted organs. And so I don't know what's going on with the slides, but I'll do my best. And so I'm going to walk through how some of these T cells or thymocytes mature. And so you have an immature thymocyte. They then go to the thymus, like I said earlier, and then they participate in something called positive selection, where they essentially are seeing if the cells can recognize self. And if they do, then they pass the test. And then they undergo negative selection. Do the cells actually bind too strongly to self and could elicit a much stronger response? And then if they bind too strong, then they also get eliminated. And so you kind of have this Goldilocks of you want to make sure that they can recognize self, but not too much. And so oftentimes we're thinking about this in the context of different diseases. And so if you, when your immune system mistakes self as not self, you can end up having an autoimmune disorder. And so that's essentially your immune system attacking your own body because it does not recognize itself as self. Some of the examples that I put here are rheumatoid arthritis and also lupus. Those are just two of many. And then for me, because I study cancer, I would like to think that also it's very hard to study cancer and target it sometimes because technically the cancer cells were you before they weren't you. And so every cell in your body essentially carries an ID badge. I have little tags on here to identify them for you today. But technically, they're little receptors that sit on the outside of their cell membrane that stick out as signals. But for today, I'm referring to them as tags. Oh. I wasn't even touching anything. I can talk this talk if y'all want. Okay. All right. And so how does the body actually know who is who? And so, like I said, they have an ID badge that tells them who they are. And so your immune system has many different cells where they go and they surveil your body. So they go around and look at everybody's ID tags and say, hey, do you work here? Are you in this building? And if you are, then they let you go and you're good. And then if not, then there's a downstream process that happens for targeting these unknown pathogens. And so we're going to talk about immune systems, or immune cells at a glance. These are 4 that I'm talking about. There are many, 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 many. And so here are your cast of characters for today. So you have dendritic cells, T cells, E cells, and NK cells. So I'm going to talk about these a little bit more in depth. So you have your dendritic cells, and if you saw from the earlier photo, they look like they have these arms that are all over. And so they are around in your body, and they also kind of try to find samples of different cells or different things. I like to think of them as if they find something that is a little bit suspicious, they take a sample of it, and then they take it back with them to your lymph nodes. And so when they enter into your lymph nodes, they talk to the T cells and ask, hey, is this suspicious? Is this something that we should be worried about? And then if not, then they're okay. But if it is a little suspicious, then they turn these naive T cells into activated T cells. And so those T cells then learn more about what this suspicious antigen could be. And then they become activated and you can go and target them. And so for T cells, I think of them as trained first responders and also their helpers. There are many different types of T cells. And so a lot of the cancer therapies that are created or that are currently FDA approved are mainly targeting T cells, but there are many other immunotherapies that target other immune cells as well. But I would say T cells are the ones that are most common. If folks remember the Keytruda commercials, that's one of the immunotherapies that's quite often used, especially in my clinic too. But yes, so for T cells, one of the first ones I'm talking to you about today, they're actually called killer T cells. So they directly destroy any cells that they're interacting with that they find has the wrong ID badge. And so here in this little schematic, your T cell is on the left. It interacts with a cell that has the wrong ID badge, and then it sends toxic granules to then cause cell death or apoptosis. This is just one of the ways that they can work. You also have helper T cells, and so I like to think as these T cells as the folk that rally the rest of the immune cells to come and work. So they don't directly interact with the tumor cells like the one that I just showed you. They actually interact with a bunch of the other immune cells to get them to proliferate in order to elicit an immune response. The example that I have here for you today is a helper T cell activating a B cell, and then they proliferate, so they're growing, and then they eventually can create antibodies. And so T cells can only attack what they've been taught to attack. So if you remember the dendritic cells with their arms, getting samples, taking it back to them and telling them whatever sample this is. And then I would say that we also have other cells that do not need to be taught like the T cells do. And I'll talk more about that later. Next, we have our B cells or the antibody factories. And so earlier I did this, and this is how I refer to as antibodies. They're Y-shaped, and they're actually made to target a specific protein or antigen. So they're very specific. And so here you can see that B cell then becomes a plasma cell, and it becomes a plasma cell when it starts creating antibodies. And oftentimes what antibodies can do is if they find the specific target, they can actually surround it. That's one of the ways that they can target a pathogen. When they surround it and attach on, that's one way to neutralize the pathogen. Or they can act as a flag to say, hey, this looks suspicious. Can some other cells come and take care of this cell? And then finally, the last of the four is an NK cell, which actually stands for a natural killer cell. And so I like to think of these guys as patrolling. And I don't think this is the way that the namers intended, but when calling it a natural killer cell, they actually don't need to be informed before. So before I said that the T cells needed some information about the pathogens in the body. So these actually don't. They are able to go around looking for incorrect ID badges or cells that actually stop displaying their ID badge. And so one of the things about cancer is that cancers can sometimes get very smart and then try to hide from our immune system by taking off their ID tags. And so they don't have that receptor on their cell anymore. So that's one of the ways that cancer actually evades our immune system. And so briefly, this is where my research actually fits in. So the immune system is definitely a very powerful system, but it does have its weaknesses sometimes. One of the weaknesses that I'm talking about today is that all the different immune cells that I just talked about, they technically have to physically reach the cancer in order to target them. But what happens if you can't directly get to that tumor? And so I think the dichotomy of thinking about tumors is you could have a hot tumor. And so hot refers to having a lot of immune cells that can actually go and target the tumor. You can also have a cold tumor where you don't have as many immune cells there. And so you aren't able to elicit a response. And so sometimes, and this is only specific to certain cancers, but sometimes tumors actually get very smart and they create a border around them so that the immune cells cannot actually get through and penetrate them. And so my research is focused on mapping those specific barriers and understanding what they are and how we can target them, but also if we can actually reprogram them in our favor so that they can essentially open the gates for us to let the immune systems in. And that is all that I have for you today. Thank you so much, everybody.
time for 2 questions, if anyone has any.
I have a million questions, but let's start with one. You're talking about, and I'll only do it. When you're talking about the different cells and how they form in your body already, when the medical profession, or I should say the pharmaceutical, when they are doing their research, are they looking for medicine that will attack a cell or will go find it or both? I don't get it.
Yes, you're getting out to the whole field in general. I think Dr. Anson will talk more about specific therapies, but you're right. You can have drugs that go to attack a cell and destroy it. I think of those as they're called antibody drug conjugates. So it's an antibody like the little Y guys that I talked about. Right? They're attached to a drug, and so the Y antibodies are specific for a receptor on a certain thing. You could think about in breast cancer, they often have HER2 mutations. And so there is a drug that has an antibody for HER2, and it has this drug that's attached to it. In the clinic, I've heard it called to as a payload, essentially. So you get the drug there, and then once it's there, then it releases the drug to the tumor cell. So that's destroying. I talked about Keytruda briefly, or pembrolizumab. That one is thought to kind of turn on your immune system. So cancers are very smart in very different ways. One of the ways is that you can actually get immune cells to your system. So it looks like it could be a hot tumor. So there's a lot of immune cells. But actually, when you look at them a little bit closer, they're all there, but they're actually exhausted or tired. So they actually don't work. And so one of the drugs, pembrolizumab, is thought to reinvigorate them to get them to be more active. Yeah.
So nice talk. I have a question. So I don't fully understand. So in a cold tumor, sometimes the tumor might have an environment that can suppress immune response. And actually, it's not only barrier. What cancer cells do to suppress immune response?
So the question is, what do cancer cells do?
Yeah,
to suppress?
environmental cells, or like cancer environments that suppress immune response. What actually is going on there?
Oh gosh, yes. If I could give you the answers, we would be able to cure cancer. So, as you know, I only talked about 4 immune cells. There are many, many more. And you're right. Whenever we're thinking about where the tumor is in the body, they call it the tumor microenvironment. We understand that wherever the tumor lives, the area around it is also a little bit not normal. And so they actually work in conjunction with each other. So the tumor cells are talking to some of the immune cells. They can actually use some of the immune cells to their advantage. So they're essentially recruiting them to their side. And then they release these signals, or if you've heard, cytokines, to try and stop other immune cells from coming. One of the other ways that cancers are also very smart is they create hypoxic environments. And so that's where you don't have enough oxygen. And so they actually prefer that sometimes because they can work a little bit better than your normal cells that need more oxygen to survive. So they're very good at adapting, but then they can also send a lot of signals to other cells. And so I told you my research is focused on kind of those cells that can create the wall. So I think that the tumor cells are talking to the cells that create the wall, and they say, hey, we would like to create a barrier. And then they convince them to create a barrier. And so that's how that works. But you can imagine that this could go layers out to many of the other different cells.
Question, does the immune system development over the course of your lifespan change as you get older? Does it decline? And then follow-up question would be, are there specific supplements that can help to boost B cells versus T cells, and things that we can do to give ourselves the best chance?
Yeah, so I would say that your immune system does change as you age. It also becomes more educated, I would say. You're exposed to a lot more things, and your immune system is better able to respond to a lot of pathogens. In terms of if you can boost your immune system. I actually think Dr. Snow will be talking a little bit about that during his talk.
Stay tuned.
Thanks, everyone.
Thank you so much, Emily, for that wonderful warm-up talk. Next, we have our faculty speaker, Dr. Anson Snow. He is a hematologist, oncologist, assistant professor in the Department of Hematology at UNC, and a member of the Lineberger Comprehensive Cancer Center. He completed his undergrad at Pepperdine University in California and then attended medical school at the University of Colorado. He completed his internal medicine training at USC in California and then his HEMONC fellowship at UNC. In the clinic, he treats patients with different types of blood cancers, including leukemia, lymphoma, myeloma, which might require a stem cell transplant. His research focuses on therapies that help prevent relapse in acute myeloid leukemia after a stem cell transplant. In collaboration with other researchers at UNC, he is developing a post-transplant mRNA vaccine for patients with acute myeloid leukemia. He is also involved in multi-center clinical trials studying other cellular therapies aimed at preventing relapse after stem cell transplants. We are grateful to have Dr. Snow with us today and look forward to learning more about the immune system, cancer immunotherapies, and the exciting advances being made in this field. Dr. Snow.
Oh, no, Kyle.
Well, thank you so much for having me. It's a wonderful portrait of myself. So selected that for this talk. I do want to recognize, first of all, the students who put this on. I think it is quite a big effort on their part to try to inform the public about the different medicines that we have available for people, the disease processes, and they're very early in their career. I think this is a very rewarding thing for them to do, especially when they get to talk to people, especially as they start their careers, actually start treating patients. I think they find the education part and doing seminars like this, once again, very rewarding. So thank you for coming. I think we should give them a round of applause. So my talk today is about immunology and immunotherapy. So really the process of taking treatments and trying to turn your immune system into the cure. Now, there is a lot of talk about, how a lot of new drugs that have come onto the scene. I think there's a lot of excitement, enthusiasm for the current age that we live in. I would say as a treating physician for patients, specifically, I treat patients with blood cancers and I'm a bone marrow transplant physician. And so our jobs with a bone marrow transplant is to try to take a new immune system from someone else and put it into another person with the hope that they can get their cancer cured from that new immune system. So, I deal with this on a daily basis. I see, talk to, and treat my patients. And so hopefully I can give you a little bit of understanding of the depth and the broadness of all the new drugs that are now available. It's an exciting time to be a hematologist and an oncologist. I think it's more exciting for our patients because we have all of these new advances. And a lot of these advances have only come in the last decade or so. And the new treatments that are coming out so rapidly, which is really exciting. Especially for cancers that may have not had treatments before. So hopefully you find this talk entertaining and also informative. So the title of my talk is, What if the cure was inside you all along? So the topics that we'll plan to cover today are immunotherapy, the history of immunotherapy, how cancer evades the immune system, the different types of immunotherapies, their side effects, their limitations, and then the cutting edge, where immunotherapies are going to be moving forward in the future. And then we'll end with our Mythbuster session by probably you will find that the most interesting, and probably the most applicable to your daily life. So what is an immunotherapy? So it's a type of therapy that uses substances to stimulate or suppress the immune system to help fight disease. So we have been using immunotherapy for a long, long time. So starting back in 200 BC, the first reported immunotherapy was started in China. And so what they did is patients who had smallpox, which was a very deadly disease at that time, they would take the scabs and the pustules of the smallpox patients, grind it up, put it into a long tube, and then blow it into someone's nostril with the hope that they would get the infection, but at a very mild, but hopefully a very mild infection. They would get protection after having that virus exposure. Now, the issue was, this was a radical idea, right? You could imagine at the time trying to sell this to one of your patients. Hey, I'm just going to give you this disease. Hopefully you'll be okay. By the way, you might die from it, but not a big deal. Let's just try it out because you might not. Good luck. But the insight from this practice really sets the foundation for everything that follows. So moving forward, immunotherapy really didn't enter the world of oncology and cancer care until the late 1800s. So there was a medical surgeon, his name was William Cooley. So he treated patients with metastatic sarcomas. And at the time, the treatment for sarcomas was to cut out the cancer. So you can imagine if you have a sarcoma in your leg, you would lose your leg. And so he noticed, though, that patients who had severe bacterial infections sometimes would have regression of their tumors, meaning their tumors would shrunk. Sometimes they'd be cured. And so what he came up with is called Cooley's concoction or Cooley's toxins. And he took some of these bacteria and injected it into these sarcoma tumors and found that they actually shrunk at some of these patients. He published this work, and if you have time to read on your own, you can actually pull up the article that he published back in that day. And at the time, it wasn't revolutionary. People said, I don't know what you were thinking, this is crazy, and it kind of fell by the wayside. And it isn't until the 1950s where the idea of a stem cell transplant started to take hold. And really has some sad history in terms of the origins of stem cell transplant. Really, it comes out of the days of World War II when we dropped the bomb on Nagasaki and Hiroshima. And what they noticed is that patients exposed to high doses of radiation had no immune system. The patients who had survived that kind of on the outer edges of the blast would come in, they'd be deathly ill, they had no blood cells, they would succumb to infections, and they didn't really understand why. And so they looked and they said, wow, these people don't have an immune system, they don't have blood cells. And the reason is the radiation they got from the bombs nuked their bone marrow. So that's their blood making factory. And so from that, people decided, well, or tried to understand, can we recover the bone marrow? And from that work, they found that you could potentially transplant a new immune system in patients who no longer had a bone marrow. And that's where the idea of a stem cell transplant came in. So as you can see here, the idea is that you take the immune system of a healthy donor, and you have this collection of cells, which include T cells, NK cells, dendritic cells, B cells. These are all the cells that Emily talked about in the beginning of her talk. And you give the patient who has the cancer some type of chemotherapy to wipe out their immune system. And then you infuse that new immune system into the patient with the hope that that new immune system will go out and seek the cancer and destroy it. So moving into the future and talking about immunotherapies, I think it is important to understand how cancer develops. Now, this is a very basic, rudimentary understanding of how it happens, but I think it gives a good understanding for most people of kind of, this is how we think cancer evolves. So everyone, when they're born, has normal tissue in every part of their body. But over time, depending on different environmental effects, so let's say you're exposed to lots of pesticides, chemicals, or you have a genetic predisposition. So let's say people who have a disposition to getting breast cancer, people probably familiar with BRCA2 or BRCA1 mutation. This means that they fundamentally in their cells have a predisposition
to develop a cancer. And what happens over time, especially as you age, your cells also deteriorate. And when they deteriorate or if they get these exposures, they develop mutations or abnormalities in the genetic code. What happens is normally your body is able to recognize those cells that have developed those wrong genetic codes as bad. That says, hey, I need to get rid of it. So it gets you back to kind of the starting point. However, over time, some of those cells develop the right mutations where the immune system can no longer recognize it. And as Emily mentioned, the idea between hot and cold tumor is kind of the same idea. There's a hot cancer cell that is easily recognized by the immune system, and there's a cold cancer cell that is not. And it's those cold cancer cells that start to proliferate over time, and they escape the immune system that is trying to get rid of those cells, and they start to proliferate into a tumor. And so that tumor, I want to once again recognize that the tumor isn't just a bunch of cancer cells, but there's a lot of cells surrounding that cell creating the ecosystem. That includes different immune cells, blood vessels, there are different chemical signals that these cancer cells release to say, hey, I need to grow, leave me alone. And so the cancer hijacks this local environment to protect itself and suppresses the immune system from trying to attack it. Cancer cells are remarkably smart. They have developed different ways to prevent the immune system from recognizing it. So I think of it as a three-pronged system where they camouflage themselves. So they actually hide the ability, or as Emily said, flip their badge around so no one can really recognize who they are. They can coerce the immune system to say, hey, I'm okay. Don't bother me. Here are some things that make you happy. Don't attack me. Or they create that environment that we was talking about, that barrier that really protects them from having infiltration from the immune system to actually get rid of those cancer cells. So understanding these escape tricks and these mechanisms have allowed scientists to design therapies that undo that process. So that's where we get into immunotherapies. And so in the words of Mugatu, immunotherapies are so hot right now. If you talk to any oncologist or any hematologist or anyone treating anyone in the cancer realm, but also in the autoimmune disease realm, immunotherapies really have been a game changer. So I'm going to start discussing some of the different immunotherapies that have come about over the past decade. And once again, this is kind of a brief overview of things. There are lots of different therapies that I'm laying out, but I'll try to focus on the main ones. So one of the big immunotherapies is called monoclonal antibodies. These are lab-made proteins that are made to kind of work like guided missiles. They're designed to recognize and latch onto specific targets or cancer cells. And depending on how they are built, they can flag the cancer cells for destruction, which are checkpoint inhibitors. They can block tumor growth, which are bispecific antibodies, or they can deliver a toxic payload directly to the tumor to kill it. These are antibody drug candidate conjugates. So starting with the checkpoint inhibitors, I'll draw your attention to the diagram on the right. So in a normal immune system, you have your T cells that are floating around, and if they engage with a cancer cell, usually what they'll do is they have a receptor that recognizes and says, hey, is this me or not? But the cancer cell is smart, and it has its own mechanism and own receptors that are actually cross-talking to that T cell to say, hey, I'm okay, leave me alone, we're cool, let me be. And so some of these receptors that you'll hear about are called CTLA4 or PD1 that recognizes receptors on other cells called PD1, PDL1, and CD80. What they do is they work as the brakes on the immune system. And so scientists have developed antibodies that target those receptors and block that interaction, and it blocks that brake. So when you block that brake, the T cell then is able to recognize the cancer as bad. And over the years, there have been 9 FDA-approved checkpoint inhibitors that have been developed, and there's more in the pipeline. pembrolizumab or Keytruda. You've probably seen a lot of ads over the years on your television for this particular drug. I think because it's one of the first ones. Has a lot of different indications, 35 to be exact. And if anyone is familiar with the story of Jimmy Carter, so our 39th president, it kind of demonstrates the power of how powerful these checkpoint inhibitors are. So advanced or metastatic melanoma really was a death sentence for patients. And in 2014, pembrolizumab came on the market, became FDA approved. In 2015, Jimmy Carter was diagnosed with melanoma and was found to have metastatic disease to his liver. So they saw those lesions, they cut out those lesions, and then unfortunately, they saw that it progressed to his brain. And at the time, pembrolizumab had been on the market for about a year. So they started him on that treatment, and given at that time he was 90 years old, started on this treatment, had 4 cycles of this checkpoint inhibitor, and his tumors regressed. He was in a remission. And as you can see, he passed away in 2024. He had many, many years after having that treatment. You can see the profound effect that these immunotherapies can have on a patient's life, really change them. The issue is that when you turn on the immune system again, there are problems. So you can think of checkpoint inhibitors are the release brakes on the immune system, but when you release the brakes, we're not very good at releasing the brakes just a little bit. We kind of let the brakes off all the way. And when you fully release the immune system, it can attack healthy tissue. So here in the middle, there's a diagram showing that the T cells that you want to fight the cancers can proliferate sometimes out of control and start to attack your normal tissue or your normal organs. There are also regulatory T cells that help suppress the immune system in a normal body. The drug is very good at down-regulating those things and also helps ramp up the immune system. And then your body can also produce antibodies that start to attack itself. And it can affect any organ in your body, going from your brain all the way to your joints. And the issue is these side effects can happen at any point during the treatment course. So we consider those the acute side effects. They can happen long-term. And then even when you're off of the therapy, you can develop late side effects. So you can develop these almost autoimmune-like processes many years after the treatment. So, and they can be quite debilitating. And so there are patients who, yes, they've been cured of their cancer, but now are dealing with other side effects from the actual treatment itself. So there are pros and cons to these things. People may ask, well, if these type of immunotherapies or checkpoint inhibitors are so game-changing, why can't we use it for all different cancers? And that's a great question. And it's all cancers are not created equal. Every cancer is unique in its own biology. It's unique in its own fingerprint or its own ID badge. And so every cancer acts differently. But scientists over the years have looked at all these cells for different cancers and have been able to kind of categorize cancers that have a lot of mutations versus not a lot of mutations. And generally, the more mutations that you have, you can think of it as more things on the surface or more ID badges that tell the body, hey, this is not normal. And so as you can look at the top, cutaneous squamous cell carcinoma, melanoma, have a really high mutational burden and thus have a really good response to the immunotherapies. Whereas on the bottom, pancreatic cancers, sarcomas, don't have as many mutations. So they don't have as many surface cell receptors that are telling the immune system, hey, attack me. So so they don't respond to the immunotherapies as well, or we call them those cold tumors. So moving on, the next type of monoclonal antibody that we use quite commonly in the cancer world is a bispecific antibody. And I call these the world's worst matchmakers. And so what they do is they take a T cell and put it in contact with the cancer cell through an antibody. And when it does that, the T cell is then able to recognize the cancer as bad and kill it. So I call it the world's worst matchmaker because you end up killing the person you're trying to match it with. There are many different bispecific antibodies that are available on the market. You can see here on the figure on the right, there are many different solid malignancy bispecific antibodies, and then there's a lot of blood cancer ones that we use quite frequently. As of 2025, there are 9 bispecific antibodies that are FDA approved. Like I said, they're mostly for blood cancers, but more on the way. And then finally, the last class of monoclonal antibodies are antibody drug conjugates. So you can think of this as a dirty bomb. What we're doing is we're attaching chemotherapy or some type of drug to the antibody. And once again, it's going out, seeking the cancer cells, and that cancer cell will then take in the drug, and that drug will then work inside the cell to kill it. On the right, you can see that there's lots of different antibody drug conjugates. I won't go through all of them, but once again, many are on the way. So now I'm going to move into cellular therapies. Cellular therapies, I would think, are kind of taking the immunotherapies kind of to the next level. But I do want to reiterate kind of how the normal immune system works, just to kind of recap for you, because it's really helpful in understanding how cellular therapies work. So normally, when your body is exposed to something bad, you have these cells that are going out and saying, yes, this is me, this is that, and they take it internally and then present that thing on the surface of that cell. And your immune system will take that and recognize it as either bad or not bad. And if it recognizes it bad, it then will go out and find anything with that specific ID badge or that fingerprint and kill that cell if it ends up recognizing it. So that's what your immune system normally does. What cellular therapies do is they leverage that. And so we are able to remove the immune cells from patients, and then we're able to engineer them in the lab and infuse them back to the patients so that they recognize that cancer that we're trying to go after. So you can think of it as upgrading your own immune system and creating your own army to attack your cancer. And there's many different ways that we do this. So there are therapies called tumor-infiltrating lymphocyte therapies. So we actually can excise your tumor. So if you have a solid cancer, you can excise the tumor. You can remove all of the T cells that are in the tumor, because there's in the tumor there's a whole bunch of T cells that are aren't active against the cancer, but they're sleeping. Remember that the cancer cells were really good at suppressing the immune system. So there are tumors, there are T cells that are there, and you remove those T cells. They then grow out those T cells and then reinfuse them to the patients. And those T cells are very effective at killing the cancer. You can also engineer the receptors on the T cells to go after the cancer. So it can either be through a T cell receptor or chimeric antigen receptor. I won't go into the specifics of how the differences between the two, but the main point is that you're energizing and making a super T cell specifically focused on cancer cells. And then finally, you can take a whole bunch of those cancer cell proteins in a lab, give it to these dendritic cells that then present it to the T cells and kind of train T cells over time to recognize the different things that tell a cell that it is a cancer cell. And then what you can do is, once again, take those T cells that have grown in the lab and infuse it to the patient with the hopes that it will go after the cancer. There are many FDA-approved cellular therapies. There are technically 9 that have been approved since in the last decade, coming up to 2024. I want to bring your attention to Kymriah. This was one of the first CAR-T therapies that came out. It was quite significant because I can still remember it. I was in residency at the University of Southern California. We had patients with acute lymphoblastic leukemia. And at the time when patients relapsed with that particular type of leukemia and had other types of chemotherapy, really the chances of survival were pretty dim. RT came out with the idea that you could engineer these T cells and then give it back to the patients to go after lymphoma. It was quite life-changing. So life-changing that patients who had been exposed to so many chemotherapies were refractory, didn't really have anything else. This therapy was able to bring a remission to those kids about 80 to 90% of the time. I mean, you generally don't hear about remission rates that good for different cancer treatments. So really life-changing. I still remember one of the first patients that we had treated with the specific drug at that time. At UNC, we actually have a facility that can manufacture these engineered T cells. And so what we do is we have a patient, we bring them into the hospital, we take out their immune cells. We then take a virus that encodes what we can say software that tells the cell, hey, you need to make this specific receptor to recognize the cancer. We then grow out those T cells so that we have a lot of them. And then we then give the patient chemotherapy to get rid of their lymphocytes and their T cells, and then infuse those T cells that are meant to go after the cancer back to the patient. Right now at UNC, we have over 20 clinical trials that are investigational clinical trials using CAR-T therapies, from anything from cancer to autoimmune diseases. All of these have been developed on our cancer, or in our campus through our Lineberger Cancer Center. And a lot of this work has been headway by Pietro and Barbara Svalda. And so they're really our basic research scientists that have helped develop a lot of these over the years. Now, for these CAR-T therapies, although we have had successes over the years, it can cause problems. So when you give these CAR-T cell therapies to patients, it can really trigger a massive inflammatory reaction. When you get this inflammatory reaction, people can have really high-grade fever, their blood pressure can drop, they can become hypoxic, meaning they're not getting enough oxygen to their body. These patients can get really sick and end up in the ICU. And we see it frequently. However, as we get more experience with these CAR-T therapies, it's happening less and less. In addition, this inflammatory process can cause issues with the brain. So people can be confused, they can develop seizures, they can go into a coma. Once again, over the years, we have learned to combat this so that the side effects are not profound, but they still happen. And then going into the future, the more time that we've had with these CAR-T cell therapies, we're realizing that people actually have long-term consequences. So we're finding that patients sometimes develop autoimmune diseases down the road. They can develop neural problems where they develop like a Parkinson's-like disease. Later on, they can have issues with their guts. They can have issues with their immune system, where their immune system never really recovers from the therapy. So once again, these therapies are really exciting that they're available for patients, but they do come sometimes with a cost. So the next thing I'll talk about is cancer vaccines. This is something near and dear to my heart. It's my research focus. And so everyone I'm sure is familiar with vaccines and getting vaccines as a child to prevent different infections. And so we usually consider those types of vaccines preventative. The idea is that we are training the immune system to respond to a certain target, and when in the future, if your body sees that target, it goes after it. So let's say measles, since it's been in the news a lot. When you get your measles vaccine as a kid, the idea is that you're training your body to recognize measles at some point in the future, so that when it happens in the future, your body can see it, recognize it, and destroy it. And hopefully, if you do get measles, you don't get as sick from it because your immune system is helping to protect you. What I am more focused on is the therapeutic avenue of cancer. So trying to train the immune system to actually go after the cancer cells. And in this process, you already have the disease there. And so we're trying to get the immune system to respond and go after it. Therapeutic cancer vaccines have been in development for over 50 years. And yet, after 50 years, we only have 3 FDA-approved cancer vaccines. The question is why? So there are a lot of variables that go into cancer vaccines and why they haven't been efficacious. I'll go over a few of them, not in too much detail, but kind of give you an idea. Wrong timing. So a lot of times when we give cancer vaccine, we give it too late in the disease process. Vaccines, in my belief, really are good at preventing disease when there isn't a lot of it. When there's so much disease, remember the cancer is very smart. It has created that barrier, it's created a city that has its defenses, and the vaccine is not able to train the immune system that can evade it and go after it. That's one issue. Manufacturing and costs. So a lot of these vaccines back in the day could cost a lot to make. In addition, people were looking at personalized cancer vaccines, and when we make a personalized cancer vaccine, that means that vaccine is tailored to that individual person. So you can imagine there's a cost entailed with making a specifically tailored medicine to you. In terms of vaccine technology, the technology was kind of based on what the old vaccines were using, and we've come a long way. And cancer, of course, is smart. It has found ways to outmaneuver the immune system. So just giving a vaccine may not be enough on its own to prevent the cancer from going away. And then a lot of these vaccines targeted one thing. You got to remember that a cancer cell has many different targets that the immune system can go after it. And if you train the immune system to go after one target, the cancer cell is smart and finds ways to evade that one system. So really, probably the most effective cancer vaccines are ones that can go after multiple targets. So I like to make this analogy of building a house and how cancer vaccines should work. So, a foundation isn't a house. There's many different parts that go into the house. You have the foundation, you have the plumbing, the electrical wiring. You have the framework, and you have a lot of specialists working together to build that house, right? You have the contractor, the plumber, the electrician. You have the city coming out to make sure it's up to code. And so the same thing with a cancer vaccine. So that's where we set out to tackle a task in terms of trying to prevent relapse in acute myeloid leukemia. So acute myeloid leukemia is a very aggressive blood cancer. It's really hard to beat. It is one of the most common leukemias patients in the elderly. So the average age of onset is about 68 years. What happens is your bone marrow fills up with these abnormal cells and crowds out your normal bone marrow cells, which includes your red blood cells, which deliver oxygen to the rest of your body, your platelets that cause your blood to clot, you have a cut, and then your white blood cells, which are your immune cells. Even with the best treatments that we have available today, many of these patients will not be cured with chemotherapy alone. They have to move forward with a bone marrow transplant. And the issue is a bone marrow transplant can be quite intense. So not everyone is a good candidate for it. If someone is lucky enough to get to the bone marrow transplant stage, the biggest cause of relapse after a bone marrow transplant, or the biggest cause of mortality and death, is relapse of their disease. And this is a graph demonstrating that the earlier you relapse, so this bottom line here, if you relapse in the first 6 months after your transplant, the probability that you will survive out to a year is less than 10%, really abysmal. The longer you survive, or the longer it takes for you to relapse, the better your overall survival is, the longer you live. And so this has become one of the most important unsolved problems in the transplant work. So our thought was, why couldn't we just train that new immune system that these patients have to finish the job? So before you go to a stem cell transplant, you have to have very good control of your cancer. Meaning there shouldn't be any cancer detected based on the most sensitive testing we have available to test for that cancer. So these patients really don't have a lot of burden of disease, which is great because, once again, thinking of that tumor microenvironment and that barrier, when you don't have as many of those tumor cells to create that, hopefully that's the most opportune time to go after it. And with a healthy immune system, once again, you don't have the issues with that immune system being fatigued. Most of the new immune systems come from younger donors. So these donors are generally under the age of 35 or younger. And so you can imagine it's a fit immune system that we're working with. And so our thought is, could we use an mRNA vaccine very similar to what they used for COVID to train the immune system and specifically those mutant T cells to go after cancer? And so our lab's focus is doing that. And we have found different targets that can actually do this. So we have done the experiments and we have found that an mRNA vaccine can actually stimulate the immune system to go after cancer cells. The biggest question is, can we start to personalize it, or can we have a universal vaccine that can potentially give benefit to all stem cell transplant patients? So that was a little bit about the research that I'm doing, and I want to kind of talk about what the future of cancer immunotherapy holds. So I don't know if anyone's ever watched Star Trek, and if they ever recognize the machine that they would use on the ship, the tricure. And so they would take this machine and they would wave it over a patient, and that machine would say, hey, you have this, this, and this. This is what you should do. I do think that the field of oncology is moving towards that. We are having a better understanding of the biology of cancer. We have a better understanding of the biology of the patient itself and their immune system. And I think we're going to start to combine all of that, especially with the advances in AI and machine learning, combining all of that to tailor therapies for patients. So I think we'll come to a point where we would use all the information from our diagnostic testing to say, hey, this cancer therapy probably is the best for you, or for someone else that has a different ethnicity, for instance, because they might metabolize the drug differently. We would say this is the best drug for you. And I think we are moving towards that, but it is going at a very slow snail's pace, I would say, because the world of the immune system in cancer biology is extremely complex. Another thing that we're starting to realize is nutrition is probably important. And a big hot topic in the world of cancer is the gut biome. So in your gut, you have a lot of different types of bacteria that are living in your gut. You can think of it as a living organ. And probably what you're feeding the microorganisms in your gut probably may have an effect on how your immune system functions or just how healthy you are. There are probably certain bacteria that are more related to people with better health outcomes, maybe less cardiovascular disease. In this case, this was a study done by scientists showing that if you ate more fiber and had a high fiber diet, you were more likely to respond to immunotherapies. And it was dependent on what kind of bacteria really thrived in the gut with that high fiber diet. As time goes on, I think we will start to have a better understanding of this. But once again, we are kind of at the beginning of this. And so, would I tell you to go out and, buy a bunch of fiber and eat that every day so that you live longer and healthy? I think there's a lot more nuance to it, and we don't really quite understand the science and what bugs are probably the best. But I would suggest to patients, and this is what I suggest in my clinic all the time, is that it is not wrong to exercise and to live a moderately healthy life. Meaning that anything that probably comes out of the box probably isn't good for you. You should try to eat fresh, natural foods in order to hopefully help prolong your life. Now, once again, I also tell patients that a lot of this may be determined by your genetics. Some of it is out of your control. No matter how good of a diet, how much exercise you do, and I see this in my clinic, there are many young patients who come into my clinic with cancer and ask, what did I do wrong? Or why did I develop this? And I tell them, I don't know. I don't think it was anything that you did. You don't have any mutations that necessarily say that this was passed down in your family. Sometimes all I say is that this came down to bad luck. Now, in the future, we will find out that these patients had certain mutations that predispose them to these cancers, but at this point in time, there's still a lot of unknowns. I also want to emphasize that in terms of curing cancer, there isn't a single bullet. And I want to emphasize this in some breakthroughs that have happened. So people are probably familiar with the mRNA vaccine, the COVID mRNA vaccine, and the two companies that came out with that were Moderna and BioNTech. People always wonder, how did they come out with a vaccine so quickly during the pandemic? The reason being is that those companies were cancer therapeutic companies focused on creating cancer vaccines. They have 20 years of research developing these technologies to try to cure cancer. And what did they do? They just pivoted to say, well, why don't we just use it to go after these viruses? And it worked extremely well. So people say, oh, these therapies came about suddenly. No, it came about after decades of research from these companies. But this is a really promising thing. So they have found that if you add an mRNA vaccine to patients who get surgery plus chemotherapy plus immunotherapy, that checkpoint inhibitor, and then give a vaccine on the back end, we may be potentially curing people of pancreatic cancer. I'll remind people that pancreatic cancer is one of those cancers that we consider a cold tumor. Hasn't really had a lot of therapy this work. And if you get pancreatic cancer, even if you catch it early, a lot of times can be a death sentence for patients. It's still early, and this is just the phase 1 clinical trial, but they are moving this into a phase 2 and later trial. Some of those patients were cured 6 years out from getting this treatment. And that is amazing. But once again, it emphasizes the point that, there probably isn't going to be one therapy that cures a person's cancer. It's probably going to be multiple modalities, lots of different treatments working together on different avenues of cancer to really get rid of the cancer. And then finally, I want to end with the cost. So I want to recognize, yes, it is an exciting time to live, especially as an oncologist and as a patient having so many therapies, but these therapies are expensive. Checkpoint inhibitors, just to give you an idea, are the cheap immunotherapy on the block. It costs about $180,000 per year while you remain on that treatment. Bispecific antibodies, to give you an idea, is about $220,000 per year. Same around cost for the antibody drugs. But CAR T therapies at least cost about $500,000 for infusion. And then all of the toxicities that can happen, the hospitalizations for infections or complications, can lead up to total cost of close to $1 million per year. So these are not cheap drugs. And so it's something that we're going to have to think about as we're treating older patients or patients who have these cancers. How do we target the right patients for these treatments and make sure that we're getting the biggest bang for our buck? This kind of emphasizes the cost. So in 2001, and this is still earlier, so that was 5 years ago, we have more immunotherapies available. 12% of cancer patients receiving immunotherapy accounted for 36% of the total oncology medical spending in the United States. That's a significant chunk for a small amount of people getting immunotherapy. And now even more patients are getting immunotherapies in their frontline or relapse. So this will become a big problem moving forward when I'm thinking, how are we going to pay for this? And I don't have an answer. So the Mythbusters. So the first myth, cancer means that your immune system failed. So not true. Cancer is very smart. It hides from us. It suppresses the immune system so that it can't recognize it. It's not a failure on your part. It's that you're being outsmarted. And so immunotherapy is trying to level the playing field, not trying to fix a broken immune system. And 2, immunotherapy equals chemotherapy. So chemotherapy is a toxic drug that doesn't have any specificity to it. It kills normal tissue. It kills cancer cells. It can make you very sick. It's the traditional thing that you think about when you are getting treatment for cancer, right? You're in a bed, you're nauseated, you don't feel well, you don't want to do anything. That is chemotherapy. Immunotherapy is like a precision missile. We are trying to recruit the immune system to attack the cancer cells. But of course, like I said, there are issues with that. Immunotherapy is natural. There's no side effects. So once again, the idea is that we're harnessing the immune system to really go after these cancer cells, but there are issues. It can affect many organs, and once again, it can be quite toxic to patients. The idea that you can boost your immune system. So, I tell patients, yes, the immune system isn't a muscle that you can train to get better. Your immune system is actually quite smart and has been quite adaptable since birth to protect you from a lot of things. There aren't really any supplements or foods that can really help to make your immune system better. But like I said, there is good evidence that if you eat a good diet, you stay away from processed foods, you exercise and try to hit the maximum limit for exercise, which is 150 minutes of moderate exercise, those patients just live healthier. And that probably has an effect on how healthy your immune system is. Now, can you do what some tech billionaires are doing and take all these blood tests and optimize your diet so that you don't have issues down the road? And once again, just to reiterate the point, I have seen the healthiest patients come in with a cancer diagnosis. They did nothing wrong. They were marathon runners. They were triathlon. There were people who didn't eat anything processed and made me feel shameful of what I was doing in my own life, and they still developed cancer. And so I just tell patients, at some point, a lot of this is out of control. If you like that glass of wine, have that glass of wine. If pizza brings you happiness, have pizza with your family. I think everything in moderation is important. Immunotherapy works for all cancers. We talked about that. Cancers are not created equal. Every cancer is unique, has its own biology, just has different therapies that may work for it. So there isn't a panacea for all cancer. Once again, eating certain foods can cure cancer. I wish that were the truth, but otherwise I'd be recommending that rather than some of these therapies. It'd be a lot more cost effective, make my clinic easier. And then the idea that a strong immune system prevents cancer. There's some truth to that. If you would have a life of autoimmune diseases and your immune system really wasn't normal to begin with, yes, maybe you may be more out to getting cancers or other diseases. Or if you're on different medications that suppress your immune system, yes, it may predispose you. But once again, there is no panacea. There is no thing that will make your immune system better. Some of it is just luck of the draw, and you've noticed and probably know people within your own family who lived really long lives and didn't, lived the healthiest life and still did quite well. I think we will learn more as we go on, and we'll understand why some of those people had such healthy lives, and maybe we can change and manipulate our own cells in the future. But until that time, once again, there really isn't an easy fix for this. I do want to acknowledge everyone who's worked with me over the years, specifically my mentor, Paul Armistead, and then my collaborators, which include Lidlin, Sally Hunsucker, Karen McCullen, Kathleen Reddy, who was an undergraduate who came to my lab at Hall. And then our collaborators, Ricky Liu, Ying Wang, and Rev Kong. I also want to say that all the research that we do at UNC and in my lab couldn't be done without different grants and people donating money to support these causes. I think people have a misunderstanding of the difference what pharmaceutical companies do for research and what universities do for research. The goal for an industry or pharmaceutical companies is to try to find a really effective drug that makes the most money. And so it's great because sometimes they can come out with blockbuster drugs that really change patients' lives for the best. Universities are trying to solve problems, I would say, and they don't necessarily go after the thing that makes money. It's trying to understand the biology of the cancer cells and understanding the mechanisms and maybe going down avenues that, like cancer vaccines, that may not be as sexy and may not make money, but trying to understand that to help patients. So I do encourage you, if you ever are looking to either visit a lab, you can always reach out to one of the scientists at UNC. We're happy to bring you around. Or if you can show up money, to once again sponsor MD PhD students when they're doing their training, or any of the newer faculty or other faculty doing great research at UNC and universities across the country. So thank you so much. Questions? Yes.
Could you tell us more about the collaboratory that you had in the last slide? Yeah. What is that?
I had gotten funding from the UNC Collaboratory, so that was money set aside by the North Carolina legislation, initially for COVID research. And at the time, there were so many COVID projects going on that they wanted to diversify the funding, so they actually ended up funding our project. But it was meant to fund translational research that would benefit North Carolinians. So that's what that happened for.
Fantastic talk. Do we ever expect those immunotherapies to like lose their patents? I mean, like, will we have a generic checkpoint at some point in the future?
Probably. So there are a lot of things that go to making generic products. So when patents expire, I believe usually it's after a decade. Sometimes pharmaceutical companies get wise and they can change the formulation to kind of extend the patents for things. So I don't know what they will do for that. I think the biggest barrier you'll find is just manufacturing costs for some. They get cheaper over time, but I think it will be a barrier for certain generics. And then also when you do a generic, there's a lot of funding that has to go to prove that it's just as efficacious as the original drug. And usually those clinical trials need a lot of patients to enroll in it. So you have to have a company that sees that there will be profit in it, in addition to, not bankrupting their bottom line. So we'll see. I don't know. Maybe there will be. Yes.
Is this something that you feel like the federal government should take a lead in? We can afford it.
Yeah.
And coordinate. Yeah. For the development.
So I would say we live in a unique time.
I'm talking about a real federal program.
So I think we have to understand the benefits and the limits of certain immunotherapies. I do think CAR T therapies are very exciting, and some of these immunotherapies are very exciting. The issue becomes at what point to kind of not to kind of devolve it to a singular thing, but I think how much do we think one person is worth? Is it worth $1 million to invest to get a treatment to that person, or do we need some equity or an equitable treatment that can benefit a larger population? So I think there's a lot of ethics that go into that. It would be great if the government funded every project like this, but I do think at some point, like I showed you, CAR T therapy, for the development of CAR T therapies, there are millions and millions of dollars that went into trying to develop that drug. The cost to actually give that patient and kind of the downfall of even treating the patient, if it's $1 million plus per patient, and that doesn't necessarily mean they're cured of the cancer, is it worth it? I think that more financially savvy than the ethics, and a lot of stakeholders need to be involved to kind of determine what is the right thing. Do I think it is important to fund some of these things? Yes. But I do think that we need to be judicious about it. I just don't know the right answer. Yeah. Definitely.
I hope that this question hasn't heard much what you talked about. Is plasma donation still a thing, and is it part of the immunotherapy picture?
Yeah. So plasma donation or even blood donations, etc. they're not really a part of this, I would say, but we do use some of those things um, to help mitigate certain processes. So like we can collect immunoglobulins from patients and we use that for different autoimmune disease therapies or to prevent infections and translocations. That comes from the plasma. In terms of like blood transfusions and so forth, in terms of trying to take it back to the immunotherapy side, we do have to worry about, especially in blood cancer, where all the patients getting two blood transfusions and so forth, developing antibodies against those things. So there's research going on about that. But in terms of, I don't know, maybe I'm linking two things, but there's a show that I always watch, Silicon Valley, Silicon Valley, where it was about these tech billionaires in the world they live in. And one of the things that they talked about was transfusing plasma from young people into, the tech billionaire to live younger lives. And the joke was that one of the characters in the show did his blood work and found out that he had high cholesterol. The sugar was really high, and it was because that young person was not the healthiest young person. But I don't think we quite understand that process. There are things that athletes are using, like plasma-rich injections to help heal from different injuries and so forth. I think we'll learn more over time and how we can use the plasma to benefit people, but I think we're still in the infancy.
So I have a quick vaccination. Several years ago, we have a pandemic, and then I did 3 times the vaccination, maybe every month. But after that, I had from the doctor that if we more than 50%, vaccination can be done. That's true.
Yeah, so the way I would tell patients is that viruses, so cancers can mutate a lot and change their genetics and how they are presented to the immune system quite frequently. Viruses do it at a much more rapid rate. It's the reason why we need a flu vaccine every year, is because the flu virus mutates so often. And we'll try to predict every year which flu virus may come out. And they have modeling and so forth, way above what I understand. But they try to predict what would be the next flu virus that will go after people. And so that's why you have to have a new vaccine every year, because the virus is changing so much. Same thing with COVID. It's a virus.
Ideally, maybe the vaccine, but it's different. So, but if the debate, second time, 3 times maybe or boost, but up to the 5th, 4th, 6th, or 7th, maybe come down. So we produce antibody.
Generally, the vaccines, each time has changed. So it's been going after a different virus. So the virus has a new protein that the mRNA vaccine is trying to train the immune system to go after. So that's what each vaccine. Now, in the beginning, you're right, there were some vaccines that were used as a boost because they were trying to boost against that specific thing. Now, each COVID vaccine that comes out is trying to target a new variant of that virus. So technically, you may be protected from the virus that you were originally vaccinated from. And if you saw that one again, hopefully you get a viral illness and wouldn't end up in the hospital. But if you got infected with a different COVID virus that had a different signature, then you could get sick, even if you were vaccinated, because it's a totally different virus.
I know one question about the antibody. The skin, sometimes I inject the the antibody for eyes. I don't know why exactly. So I think the human antibody, but so when the company develop and then to test those antibody in the preclinical testing in the animal, do they also accept human antibody or maybe mouse antibody? No.
Yeah, I mean, they can use mouse antibodies or human antibodies.
For preclinical test.
for preclinical tests. Well, even the antibodies that I showed you, some of these are called chimeric antibodies, meaning that some of it comes from an animal and some of it comes from a human, or some of it may just be totally humanized, which is why when people get these infusions of these antibodies, they can have reactions, like an allergic reaction. So depending on what drug you're giving, you monitor those patients very closely for those reactions. And if they do, we can give them medicines to help prevent really severe anaphylactic reactions. So yes, good question. I don't know specifically which, there's lots of them. Yes.
Thank you for the talk. It was a very dense topic, complicated topic. Thanks for breaking it down for us. You said a couple of times, I think, that in the last 10 years, the number and types of therapies has increased dramatically. I think that's sort of what you talked about.
Yeah.
I think it wasn't just CAR T, it was multiple types of therapies, right?
Yes.
But in general, what I'm wondering is, in your opinion, what has led to this acceleration of breakthroughs in the last 10 years?
Yeah.
And sort of our two-part question, sort of what do you foresee happening in the next 2 years? And talking about AI and sort of maybe the role that may play out here.
I would say follow the money. And I think these companies are making a lot of money from these new immunotherapies, and they're working. I think the biggest thing is having that first blockbuster drug. When you find out something works, then generally the pharmaceutical companies like to go after it and put their money towards it. Cancer, I would say in general, I think everyone, when they hear the word cancer or if they have a family member that develops cancer, a lot of people have this gut sinking feeling, right? This is a problem that I need to fight. I need to go after. I need to find therapies that will cure this. And that's what they're really focused on. And so it's a little bit different with heart disease and other diabetes, et cetera. There's almost an emotional attachment to cancer. And I think there will always be money that's funded towards it compared to other diseases. I mean, if you look at a good idea or a good analogy I always tell people is that infectious disease, right? Infections have been around for a long, long time. Infections can be very dangerous, and they can threaten someone's life. But there isn't a lot of research or money that goes into it. There aren't a lot of new antibiotics that go into it because there isn't a lot of money in it. And also it's not as sexy. And then patients hear that they get an infection because our antibiotics have become so good. People don't really give it a second thought. And so in juxtaposition, cancer research overwhelmingly gets a lot of things because we haven't really found the answer. We haven't found that panacea necessarily. And so a lot of money is being funneled into it. And I think you will see that even in the government, you have a lot of government personnel or family members who have cancer, and they realize that they want to kind of contribute to that cause. So I think it's a combination of we've had successes with certain therapies in the immunotherapy realm. You're treating cancers, and for people, once again, when you hear the word cancer, people seem to emotionally get invested behind it and work together to try to hopefully get rid of it. And then that brings the money. So let's just say follow the money.
Thank you.
Okay.
Thank you.